So the two dimensions of risks are time difference. That's a very important dimension of risk. And the other one, you still remember? Volatility, huh? So the fluctuation. So these are the two main dimensions of risks. So that's why time is so important in risk management. You know, actually finance is a game over time. You spread cash flows over time. That's all you do. And out of that spreading and dispersing cash flows, you make your money or not. Now, because time is so important, one of the measurements we have got to know already is gap analysis. And gap analysis, as you remember, be it a liquidity gap or be it now interest rate sensitivity gap, which is more relevant here for us, is that measures time. It measures when, at what point in time cash flows do come. And these graphs of the bars which you see give you the time dispersion of cash flows. That's what it is here. So gap measures delta T, especially sensitivity gap. So, and with gap we said we measure sensitivity, and there is a strong relationship between sensitivity and risk, as we have it here. So risk is basically sensitivity times the risk factor volatility. And that's the same as we showed in the picture, the two dimensions. You know, it's one dimension and the other dimension is like the square, which we have there in that picture, what we saw. So it's the risk factor times the risk factor sensitivity, exactly, to be times the sensitivity of the risk factor as we have it here. An example from interest rate risk. So we have here, first we have the version of a shock. So we measure a shock, delta. The change of the NPV is the NPV itself times duration of the NPV times the expected shock of the rate. That can be written in short dollar duration, because dollar duration is this here. NPV times duration, it's the dollar duration, that's the pure first derivation here, times the rate shock. That gives you the value shock. Yeah, it's very clear, huh? You shock the risk factor, which drives value. You measure how much this one is shocking. You know the sensitivity, which means it tells you how much the value itself is changing depending on that shock. And you get the shock. Very clear. Then this is the shock version, and here is the volatility version. So what is the volatility of NPV? It's the same. It's NPV times duration times now the volatility of rate. So now you get a distribution. So you have a distribution of NPV, or in short, again, it's dollar duration times the volatility of the rate. So that's how you calculate it. And that's the relationship to sensitivity, and that's why sensitivity is also quite important. Now, the last one here, what we measured here actually, you know how you call that measurement if you calculate that? What is the name of that? That's a famous measure. You know it, I'm sure. It's this one. It's value at risk. So that is value at risk. Now here I pose the question, is risk equal value at risk? So that means does value at risk exhaust the question of risk? And it's not the case, because VAR is one of the risk measurement. There are different risk measurements. So VAR is a risk, but risk is not VAR. So there's a higher category. Risk is a higher category as we have it. First of all, there are alternative measurements, like expected shortfall, we will see, or some regulatory measures, which are very complicated, but somehow they try to achieve the same, or alternative techniques, like stress scenarios. So there are different techniques, different ways to measure and so on, so we cannot exactly say that VAR is risk. Actually, there has been a lot of critique on VAR. I guess you are aware of that. First of all, the more soft critiques, the more methodological critiques are that the losses, VAR does not care of what happens in the tail, in the outside. It just tells you where the tail starts, but it does not measure it. There's another one, the non-sub-additivity, that's mainly from ETH, Professor Embrecht, he pointed that out. I'm not sure whether this is really relevant. Probably it's a point, but how important it is, I have difficulties. I'm grappling with that, I must say. Then we said there are alternative stress techniques, stress scenarios. And VAR focuses on market value only. That's another one. So it's only market value which is measured by it. And value at risk, especially the simple JP Morgan version, the normal version, is a linear approximation. The whole thing is convex, as we know that value and interest rates is not a straight relationship, and VAR often assumes a straight relationship, which makes it only relevant within a certain small area. So these are classical critiques, more on the methodology, but there is some really base critique. So one of the toughest critique is Taleb, what's his name, Nicholas Taleb, I think, yeah. He calls VAR charlatanism, a dangerously misleading tool, like much of more modern mathematized academic finance. And I think there is a point, especially if people think, math is all. So if you know the formula, we have a control over life. Then you're really fooled. Huh? But if you take math as a helping tool, and you don't stop thinking, actually a tool which triggers your thinking, so then I think it's another way, then it's different. But he criticizes those who mindlessly just, the VAR is good, okay, we are fine. So there it's really very dangerous. And I hope in this class we help you exactly to go beyond this kind of thinking here. There was the Turner report. The Turner report is from the FSA. So, and that was the report on the crisis. Here, I think it was 2009. And he says, misplaced reliance on sophisticated mathematics, which once irrational exuberance disappeared, contributed to a collapse. So he says that even things like VAR were part of the collapse. Of course, it's difficult to say, but at least something to think about, and I think there's some truth in it. And he said mathematical sophistication ended up not containing risk, but providing false assurance that other prima facie indicators of increasing risk, for example, rapid credit extension and balance sheet growth, could be safely ignored. So he said people stopped using common sense. So just using some numbers and stopping common sense here. And by the way, I really believe that risk is a tool which helps you to keep common sense going because it really models the thing. It doesn't give you just one method. It's actually a thing to help you extend your thinking, to use your brain better. And of course, it does VAR as well. Just once you have installed it, press the button and you get it. And of course, Keynes also had something to say about that long time ago, though. That was pre-crisis, but already there, I think, especially in economics, we are a little bit prone to fall into the mathematical trap. We are so proud to make it mathematical, and we forget what we really do by doing mathematics here. So he said, too large a proportion of recent mathematical economics are mere concoctations. as imprecise as the initial assumption they rest on, which allow the author to lose sight of the complexities and interdependencies of the real world in a maze of pretentious and unhelpful symbols. So he knew how to express it, but so there we have to be a little bit careful. Definitely so. So we should use it, but use it the right way. Okay, but that critique is not only on VAR, so that's a general critique of having some nice tools of measurement in a complex world where the tool is always a high simplification, and then forgetting that it is a simplification. So that, I guess, is the real danger. On the other hand, we need the simplification. We shouldn't forget that, because otherwise we are lost as well. So it's a little bit this Heisenberg thing, you try to get very precise, you lose yourself, you step away and you don't see it correctly anymore. So we always have this little discrepancy we have to live on. Nevertheless, we are still going to see how VAR is calculated. So we start with the risk factors R. So now this is the whole space of risk. This is the risk space. And we assume it's normally distributed with expectation 0 and following the covariance matrix sigma. So the sigma describes all variations, volatilities, and correlations. A big, huge matrix. I think you can see it in RISPRO. Yanis, is it visible? Is it still visible, the matrix, the market matrix? So I think you can see it really as a matrix there. You might have seen it already. So then, value at risk is the volatility of the change of value. So how much we have a certain value today, how is that value going to fluctuate? And how does it distribute at the end of the day? Which is nothing else than this matrix. So here, this variance-covariance matrix, times the sensitivity vector. That's all. What is then one element of this vector di? That's just one of the elements. D is a long vector. Now, in your case, if you have two currencies, only two currencies, and you have about, let's say, 10 points on the yield curve, and you have FX markets, and you have at least one stock market, so you are ready about your vectors about 25 or 26.7 long. If you have 10, 20 currencies, it's getting longer and longer. So the dimension of this vector can be easily 400. So that's normally in banks. So you have about 20 currencies and a lot of points on the yield curves and so on, or maybe even two yield curves that doubles it again. So here, that's what you have in this vector. And one element of that vector is that's the risk factor I, no, that's the position I times this. That's the position, how the value changes given change of the underlying risk factors, time the risk factors. That's, you have to know. So it's time that risk factor. So that gives you the sensitivity as it's defined. Just to maybe quickly show you how that vector looks like. So in the middle you have sigma. So that here is sigma 1, 1, sigma 2, 2, sigma n, n, sigma 1, 2, sigma 1 n, and so on. So that is, and that shows how the first risk factor fluctuates. That's the first one. Now, what could be the first? So we multiply it with this delta here, and we multiply it with delta here. And delta has all these di's. The di's we have up here, actually. And what could that be? For example, if you have only two currencies, let's say this is the CHF part, and let's say this is the USD part here. And this is then maybe the interest rate part, and this is the interest rate part of US dollar, and that is the fluctuation of the one-day rate, or the sensitivity of the one-day rate. That's the sensitivity of 1 month. That's the sensitivity of 1 year, and so on, up to 10 years. So that means all cash flows sensitive to the one-day rate, all cash flows sensitive to the 1 month rate, all cash flows sensitive to the 1 year rate, and so on. So this is the information which you find in the event list. You know, the list which you get when you do a mini-solve. Basically, you'll find that information. But this is just grouped by time. And so all which fall within 1 month go into this. All which fall into 1 year, and there's a boundary thing around, 1.5 years, and all that little problems which you have, but you put them there. And you sum them up. So then you have the sensitivities here, you have the same sensitivities here, and then you multiply it, and you take the square root, and you get value at risk. That is what's happening in the background. Okay, so that's VAR. Now VAR itself focuses on this point. It basically gives you this limit here. So you have to...
Are people starting to develop with alternative models of VAR? Because it's a really broad claim to say that all your exposure to every single risk factor is normally distributed.
Yeah.
So are people coming up with different stuff?
Yeah, I'm just starting now to show that. Yeah, of course. There have been a lot of movements there. At the end of the day, still, you're somehow stuck with this model. You improve it, huh? But yes, they improve. The one is here that VAR focuses actually on this point. Huh? So if you say you have a 95% VAR, that expresses in the sigma which you choose. You know how big the sigma is. So then you end up with this one here. So you have this value at risk. So it's this distance, basically, how much you can lose given a certain confidence interval. And now the expected shortfall says we have to focus not on this point, but on the whole area here. And basically what they do, they take the mean value of this area, which is the expected shortfall. So that means, so in case you are outside that 99 case, let's say the 1% happens, or the 5%, whatever you chose, given that happens, what is the average loss you have given that rate? So this is some progress. I'm not sure on how valuable it is, but that's rather lack of understanding from my side, I must say. There are other techniques, just to finish your question. For example, you use Monte Carlo techniques, so then you have all the problems of distributions and so on. You can have all wild distribution. But of course, then the question is, which is the right distribution? so you push the problem a little bit further out. But at least the convexity thing, all that is solved. But you calculate about 1,000 times longer. So, you see. So you have all that, and I think the good thing is to build up these tools, right? That you can have fast calculation, long calculation, that okay, the fast and the long is so much difference, you keep that in mind, That's how it's going on. Okay, now that was market risk. Now there is credit value at risk, and there are different methods to do credit value at risk. And I propose two here. There are definitely also new developments here. One is the credit risk plus method that was developed by Credit Suisse here. I just make you a little aware about the assumptions behind credit models. Now this is an analytical model. Here, an analytical credit VAR, so not Monte Carlo. And that has, of course, very strong assumptions. First of all, it has a 1-year horizon. And then it measures the net exposure per obligor, LGD. We know how to calculate that, huh? Take all the gross exposure, collaterals. So that's basically, once you have given the numbers correctly to RiskPro, it will spit that out right away. So for every obligor. And then you have an expected long-term default, which is tilde PI for every exposure. So some measurement about the expected long-term default. And now there comes a strong assumption that the variance of default is sigma is just PI times the sigma, general sigma. Of course, if it's going to be analytical, you have to work with such strong assumptions. And then you have sectors. So it assumes that every firm works in different sectors. And the sector could be automobile, tourism, chemistry, and stuff like that. Because then as a risk taker, you are linked to these sectors. That's the idea. And these sectors have states. They can be in good condition or bad conditions. And then your risk allocation is theta IK, so how much you are in this sector. And then your expected loss given the state of the sector, S here, given the state of the sector, calculate like this theta, how much you're exposed to that sector, and then the sector state divided by the expected sector state, so a mean state, you know. So if a sector is much better than normal, of course you have less default. If the sector is much worse than normal, you have more default. Huh? That's the basic idea, what is behind. And that's like an intuitive explanation of what happens. I explain it here in a Monte Carlo fashion, though the method is not Monte Carlo, but Monte Carlo is easier to understand. So we start with the mean and variance of sector K. So a sector, so this is throwing the dice for the sector. Huh? Let's say we have K sectors. And now we throw the dice, which sector is good and bad. So we can throw the dice, this sector is good, this is bad, and so on. There's a mean for every sector, and there is an up and down for every sector. So every sector is distributed here. So once then we get the sector states, which are here, these sector states, which we have calculated here. So then we can calculate this P, the expected loss for every obligor. That is from that formula. And then we assume it's a Poisson distribution. And given it's a Poisson distribution with the expected, we have everything. We have the full distribution. Because we can describe Poisson with one parameter. The expected loss gives us the mean and the distribution here. So then we can determine the Poisson distribution for each obligor. And then we can convolute all obligors, all Poisson distribution of all obligors. You have a lot of little Poisson distributions for every obligor, and the total loss is the convolution of all, just the average. You can, like the summing up and dividing by the number of participants. And this now is repeated for many different states of the sector. We have thrown at the beginning the state of the sector. And that gives you one distribution, given a state. And now you throw a lot of states. And now you get again a lot of distribution. And what you get is this convolution of convolutions over many obligors, over many states of the sectors. Is it clear? I mean, it's very intuitive, actually, the way you can understand. But it's described in the book, so you can read it again. So it's actually quite easy what is going on behind, if you think about it in a natural fashion, not too mathematic. So then it's much easier to understand. So what you get at the end is something like that. Now this is a convolution of convolution. So you have many obligors, which you convolute to one distribution, and many states which you convolute to a hyperstate. Many possibilities where the sectors can be. So given that, you get this distribution. So you have an expectation value. And for the expectation, by the way, here, you as a banker have to take the risk margin. That's the minimum of risk margin, because so much you're going to expect to lose anyway. That's your expectation. But then you have to take some additional risk capital. So where you have to add another charge, because you need risk capital. The mean is not happening all the time. Actually, the mean is happening very rarely. It can happen that you need much more capital, so you need more capital. And for that, you have higher charges then. So that's the credit risk plus calculation. And you can read it again in the book. It's described there, the algorithm which is behind this. This is credit metrics. That's another method. That's the first credit risk model that was from JP Morgan quite a while, I think already maybe 15 years or so ago, where this was introduced. The JP Morgan method depends on the migration matrix. So it takes the migration matrix and evaluates different obligors under different states. And so you throw the dice and look at the probability who will be where in all possibilities. That's what you do. This example, as we have it here, we have a migration matrix, and focus now on the state B. So if somebody is a B, so 92.7, this person will remain a B, but 2.5, it will upgrade to A. 4, it will go down to C, and 0.8, it will go down to D. That's the probability, and that's shown down here. So we see this is throwing this line B. If somebody is a B, you throw the dice, and there's a small probability that the guy will go up to A. There's a big probability that the person will remain B, some to C and some to D. And that you get by throwing the dice. It's very simple, actually, because the distribution is given here. Actually, you wouldn't even have to work with a normal distribution. You can use any distribution. It's just between 0 and 1, and you get that. So here. And so you can, given somebody has a state, you throw the dice, and you know the next state. Where could the person be? And you repeat that many times. And you repeat that not only for one, but you repeat them for all. And doing that, we have the problem of correlation. Because now, if you do that independently, then we say, oh, all my obligors are independent. But there's a little problem. Are the obligors independent? Or the other question, what makes them dependent? It's the same thing what we did already in Credit Risk Plus. How did we get the correlation played in Credit Risk Plus? How did that sneak in? With that state. We had the state, and given a state, it affected every obligor via that formula. You saw that. So, but very systematic. So if you have bad states, so all obligors which are exposed to that tend to be bad. So that's basically the idea which is behind. So the same they do in credit metrics. They take a little bit a different approach. That's the only difference. So they have a helper variable X, they call it. So that is really to model the correlation, actually. And EI is the sector index. So you have a sector index, and if the sector is bad, so all those who have a lot of weight in that sector tend to be bad. That's the logic behind. And I don't have so much time. Because I want to finish risk today, so I let you go through this by yourself. But just an intuitive explanation is you throw the dice for the market conditions, so that shows whether the sectors are good or bad. Which of the sectors is good or bad? And sector again is food, chemistry, industry, tourism, etc. So you throw the dice at any point in time. and then you use this xi, which is this helper variable, which then creates the correlation. And you will see how it does it. And then you take the exposure of the obligor at that point in time, and then you calculate the expected cash flows, collateral recovery. So this model is very, let's say, is very detailed. So it takes in the exposure, collaterals, and so on into account. And then you discount that, and then you repeat that for all obligors, and then you repeat that for many states. So all the obligors have the problem, and that happens in many states, and you get a distribution. In all the methods, what is important is the calculation of the exposure. Exposure always plays an important part, because exposure is what you can lose. So you have to know how much you can lose. So you have to be able to calculate for every counterparty what the counterparty is going to lose. And this, what I show you here, is about how RiskPro calculates that exposure. So we are here today, and these are points in time. Let's say there's a simulation step, like 2 or 3 simulation steps, going into the future. So first of all, RiskPro knows all the expected cash flows. What are the expected cash flows? What are expected principal interest payments? Other type of payments may be related to principals like prepayments, etc., etc. So these are the cash flows. Now, in the first step, it calculates the exposure at every point in time, and actually in every calculation time. You cannot calculate it all the time, so you have to take some steps. And these are the 3 points in time where we calculate the exposure here. So cash flows are discounted to these points here. So then you have basically the exposure here. And that takes everything into account. So from that, you calculate for every point, you calculate your expected PD. So how much you expect to lose. And that you get from the migration matrix. So you know what is the probability of default here, here, and here. So that takes this exposure, and that's a discounted loss, because it's already discounted times the PD gives you the discounted loss. And then from there, you calculate the discounted recovery. That's a portion of these. You're going to recover part of these things. So that is the discounted recovery, and then the expected loss is discounted loss minus discounted recovery. So basically what you need all the cash flows in the background. You need the knowledge about collaterals, guarantees, and all that. Gives you a net flow. You have to discount it, and you have to calculate the recovery. So you can imagine a little bit what is happening in the background when you push a button. So these kind of things are happening. This is an alternative way to calculate credit risk. It's actually from Solvency II. Now, Solvency II is the insurance variant of Basel II. Funny, they always have, if Basel is 2, they are also 2 if Basel. I think Basel III is now Solvency III up. Not yet, but I imagine, they're like twins. It's also more or less a copy, with a little bit speciality, but more or less, they do the same thing like Basel, more or less. So Solvency II has similar things like in Basel. Now here they want to calculate credit risk using a very simple formula. They start with the following. First of all, they have standard expected default. They say if something is AAA, then the PD is 0.2%. That's it, or 0.02%. And AA is this, and if you're B, if you're C, you're 30%. That is given, so you can't play around. Then they start with the formulas. We have to start down here. First, they calculate the Herfindahl index. The Herfindahl index is a measurement of concentration. And so they use this concentration measurement to calculate correlation. That's the target. So say, if you are concentrated to a few to a few people, then of course your risk is bigger. And if you are concentrated, well spread out, your risk is smaller. And I think that this takes 0 if it's well spread, and takes 1 if it's highly concentrated. So that's basically what the Herfindahl measure does. And then they adjust the Herfindahl measure yet, make it a bit rougher. They say they take only 50% of the Herfindahl and add 50%. So that's a security measure. I say your Herfindahl is always minimum 50%. So we don't trust too exact calculation. That is basically what happens here. And then to calculate the charge, the risk charge, which you have to take, you see that's basically depending on R. This is the distributions here. So it depends on R here, and on the distribution, on the normal distribution, n times PDI, which is at this thing up here. Whether it's A, then you have to put in like 0.2%, etc., times loss given default. Again, so the very important input at the very beginning is to know how much you're going to lose. And that's already a big calculation depending on all your positions you have. So you have to know that. So given that, that's the capital charge. So depending on that, and here we have a little graph where we can see if R is between 0.5 and 1, that's where it can be. That means here I have a highly concentrated portfolio, and here I have a highly diversified portfolio. And if something has a high rating like A or AA, then the charge is always very little. Given that formula, you can go through the formula and you will see the charge is almost 0. But it changes drastically if you have bad ratings, like this I think is B, or BB, B, C. So if it's C, basically it's 100% all the time. So means if you have a position in C of 1,000 francs, you need capital 1,000 francs. That's expensive. So that means you will need a lot of capital. But if you have a position of 1,000 francs in A's, basically your capital is 1 franc maybe or something like that, so very low. So you need very low capital because it's well spread out and it's in high quality instruments. So that's basically the mechanism which is behind this kind of calculations. Yeah, by the way, would you mind if I continue another 15 minutes? And then, because I want to finish that risk thing? It's okay? And then we make the break and then we do this other thing. Okay, now we come to liquidity risk. Liquidity is a totally different animal. And we see it in our systematics always that liquidity goes to the left and the value income goes to the right. So liquidity is quite different, as we have seen already in many times. On top of it, liquidity is a kind of ambiguous term. It has at least 2 main meanings. And one is called this, the idiosyncratic liquidity, your own liquidity, and the market liquidity. The own liquidity means how liquid are you yourself, and that means how quickly do you get cash flows. And how do we measure that, how quickly we get the cash flows? Which tool would you take from the tools you know already? The liquidity gap. So the liquidity gap basically tells you that. For that we have that. So that's more or less the idiosyncratic thing to measure. Now market liquidity is how well money flows between firms. And that has a lot to do with fear. Actually you could call that like a systemic credit risk crisis. So, and the tools are also closer actually to credit risk than to anything else, if you see it from a market perspective. So these are the two different things here. And basically, what you have to do, FSA, now there's Basel III. I read it already. I should maybe update this slide once. But it's continuing this, what happened in FSA here. So there are more or less 4 states you have to check. The state is normal state. So when everything runs well, and so on, means people behave normally, and you feel that more or less in the way your saving accounts and those highly liquid, sensitive accounts work. And you model the saving accounts with replication. And replication is part of behavior. So that's basically what you do. But even in the normal case, you have already a conservative scenario. Because in liquidity, the only test which makes sense is a conservative one. Because if everything totally normal, you always have your liquidity. Because liquidity only hits when there's a crisis. When there's no crisis, the money flows. That's basically what you have to do. So the normal is already conservative. So, and then you go to the funding liquidity. So that's your own idiosyncratic liquidity. Means if something bad happens to your bank, let's say your bank gets a bad name. Now people start, oh, you know, this bank is bad. They start to withdraw money. So what happens then? You know, how long can you keep the cash back in your saving accounts, etc.? And how good are your liquid assets? That could be long-term bonds, but which are easily liquidated. And in this case, of course, those bonds are always easy to liquidate, because the normal market functions. So you can sell them, and so you need normal bonds for that. They need not be even high quality. They can be normal quality. Now, another case is here, market liquidity. So here, maybe you as a bank are quite good. Everything is fine. But the market starts stop playing. So, and if the market stops, even you as a good bank are hit. Now, some banks profit, like the Zurich Kantonalbank. That went the other way, because everybody left UBS and went into Zurich Kantonalbank. So, because that was considered to be a safe bank. So some might profit, but many get in troubles, even if they are good. And the bad thing, if market liquidity is here, then it's difficult to sell those assets. Or you can only sell them with big discount. So if you have to do fire sales, you will make big losses there. And the big loss in selling means less liquidity, because you get exactly that less what it's less value. And the worst case is where both things happen at the same time. So you are in a bad bank and in a bad conditions. Normally there, only the central government can help you out. And the main idea is, if you should be able, in this situation, you have to be able to survive 30 days. Now that's the thing they want. Huh? So that means everything is against you. And you just try to keep the cash, to let it flow as slowly as possible, as slowly as allowed out, you know. And then you have to survive 30 days. That's the trick. And the models, if you do a liquidity model, exactly measures these days. And so that's the survival horizon. So why do they want to have you survive 30 days? So first of all, why not longer? Because longer is very difficult. Now, if everything is against the banking system, it will break down, because it's a system that builds on a going concern. So if the going stops, the thing stops. So you cannot have a system which works for all the time. Why not shorter? Why not 15 days? By the way, I find 30 days very short. Anyway, but why not shorter? Because the national bank, the central bank, has to be able to judge the case. You know, I mean, that starts and everybody is confused and everybody doesn't know what to do. So you need a time to think. So that should give you that breath that we can think it over. That's why it is. Okay, there are other risks, earning at risk and insurance, etc., operational, so we are not going into that. Then there are stress scenarios. I think we have done that already. You know how stress works. Stress is very simple. Take a condition, stress the condition, recalculate. That's all. So this you can easily do. But there are also, like from the regulators, there are official stress scenarios. Now, this is the stress scenario of solvency, but there's also one of Basel and so on. They tell you how much stress you have to assume here. And here we have an up and a down stress. You see here, the up stress says you have to check for, in the short term, I think it's 1 year, almost 1%, 0.94%, 2 years, 0.77. So that means the yield curve moves a little bit more on the short end than the long end. That's the up stress and the down stress, which you have to look at. Now, finally, the last thing I want to show you is, now we have all these models. We have VAR and stress and I don't know what, and Basel and solvency. Now these are still models, you know, and somehow we have to check them. Are they real? Do we play just with numbers? Sometimes we fear that, so there is at least some backtesting. And here what I show you is the backtesting of market and credit exposure. And in backtesting, you have to avoid two cases. So here, the model can be correct and the model can be incorrect. But the test result can be positive, saying it's good, or negative, saying the model is bad. Now, this is a good case. So if the model is correct and the test tells you it's correct, that's what we want. That's also a good case. The model is bad, and the test says the model is bad. That's good. What we want to avoid is type 1 and type 2 errors, or alpha and beta errors. The alpha or 1 error is the model is good, but the test throws it out. And the other one, the model is bad, but the test accepts it. That's the problem, what we have to solve. Now, this is a test on value at risk. Say your confidence interval is 99%, and you look at 1 year data, 250 trading days, say. So now you have a certain VAR, and you expect that your real losses are inside that VAR. Do you expect them always to be inside that VAR limit? No. In 250 days, how many times do you expect them to be outside the VAR limit? 99%? 2.5 days, roughly. Huh? You say in 99 days you are in the hundreds you're out. Huh? So in the average you are 2.5 days out. But you're not definitely 2.5. First of all, they are not 2.5. They don't exist. You're either 2 or 1 or 3. And it could be that you're only 1 there, you know, because it's all stochastic. Or it could be 4. So that's basically the test which is taken here. So you assume, the way I argued now, that was actually binomial. I argued binomial. I said, you're either in or out. The 99% case. So now if you're binomial, then we can apply the binomial formula. And that is what the thing does. It applies the binomial formula and say, if you are in 250 days and you have a 99% interval, and you even reject if there is non-zero outside, then you reject everything. Then you are prone to make 100% type 1 error, meaning that type 1 error means you reject the model even though it's a good one. Of course, if you say, I even like if there's none outside, you reject everything. That's very clear. But if you accept 0 only, then you have an 8.1% chance that this happens, and you would reject the model in 91% times, even though it's good. Okay, now we have to find a good area. You know, we expect something between 2 and 3, and we see also the big probabilities are here. For example, if we accept the model with 5, so we accept in 250 days whether there is 1, 2, 3, 4, or 5 exceptions. 2.5 we would expect, huh? But we have to expect some, allow some variance around that. So if we allow that, then with 5, actually then we reject only 4.1 of the good models. Huh? We still reject 4.1% of the good models. But not more than that. We never can be 100% sure. Because it's probabilistic. So you have to make a choice somewhere. And I think the choice in the Basel is 5 in 250 days. But you check it more exactly. Or do you know the exact number? But anyway, it's something like that. So that good models are basically not rejected. But the other danger, the more you accept down there, the more likely you're going to make a beta error, that you accept the bad model as good. That's the problem we are facing here. Yeah. Finally, the one last thing I want to do is that there's a test also for credit risk. Credit risk is very much depending on the rating and rating states. And what would you expect if you line up all people according to your rating? So here on the left you have all A's and then B's and C's and so on. So where would you expect a lot of loss? In the A's, as A's meaning good, or would you expect more in the C's? Obviously more in the C's. Basically, you would expect almost no loss on the A's and a lot of loss in the C's, or D's, here. And that's what the Gini index does. You line up all your customers according to goodness, up to 100, and in the very ideal case, you have no loss here, and you basically have all the loss over there. So that would go like that. So, but in reality, there are some losses in even the good ones. And the bigger this area is in relationship to the total area, the better your model is. So it's this area, not the total area, sorry, this triangle here, divided by this area here. That's the Gini index. And if it's 1, that means you're really good. So only the bad ones are only the last ones. And if you're 0, that means you are as good as average. If you are below 0, then you're really bad. Then you are even worse than the blind guess. So in the blind guess, you should be 0. So and that's how you test then the rating. That means you look at customers today. What do they have a rating? You look at customers next year's, and what kind of ratings do they have? And then you make these statistics. And then you can measure whether your model is good or bad. So there are some tests. And of course, the final test is whether the financial system survives or not. And how often things like 2008 happen. And that needs more than these measurements. That means, in addition, brains which are still awake and think. And maybe sometimes it's unavoidable. I think we need a crisis every now and then. That's my theory. So that's why it's totally, somehow we will drop into it. Yeah, thank you very much. And now we have a break. Let's make a 15 minutes break. Oh, is there a question yet? Okay.